All right, so with the recording going, let me first end with what I promised to end with, or what I promised to start with when we ended on Friday, which is I want to go over these two different methods of naming alkenes when you have multiple stereochemistries possible. The older way of doing so is the cis and trans method. And I gave the example of cis-2-butene and trans-2-butene. And I don't want you just memorizing those two. There are lots of other alkenes besides the two 2-butenes. But we were clear about why those two are both different compounds. You'll recall that we cannot rotate around double bonds in the same way that we can rotate around single bonds. So therefore, those two compounds are stereoisomers. And we've already defined stereoisomers. But they're different compounds with different properties and all of that. So they need two different names. And in cases like this, where you have a di-substituted alkene, Mike is muffled. Wait a minute. No, I did have it pointing the right way. Let's see. Is this any better? Oh, okay. Very good. Thank you for letting me know. Where was I? So in cases like this, where we have a di-substituted alkene, where two of the groups are H's, you have an H on one and something bigger on the same carbon, and on the other carbon you have an H on one and then something bigger. Then you can use cis and trans. The problem is it's kind of limited. But maybe I should back up a moment and just make sure we're all on the same page. I think you will agree with me that an alkene will have two carbons that are involved in the double bond, right? An alkene is a double bond, and there's two carbons in the double bond. Let's make sure we're clear on that first. And then I think you'll further agree with me that on each of the two alkene carbons, there's two things attached. There's two groups attached to this carbon, and there's two groups attached to that carbon. Does that make sense so far? I want to make sure that we're all tracking here. And it's going to be looking at those two groups that are on each of the two carbons in turn that's going to allow us to tell whether it's cis or trans, or the more general and more modern way of doing it is using this Enz nomenclature. So that's what we need to look at in order to decide whether the alkene is cis or trans in cases where that's possible, or in cases where it's not, whether it's E or Z. So in order to decide whether an alkene is cis or trans, you need to look first at one of the two alkene carbons, and you'll want to see something that's an H directly attached and something that's not an H, something bigger. And then when you look at the other one, you'll see also an H directly attached and something that's not an H, something bigger. And in those cases, you can use cis and trans. And all you need to do is look at each of the two alkenes in turn and find the two bigger groups, the two things that aren't H's. And if they're on the same side of the double bond, like we said the last time, you can draw a dotted line down the double bond if you want to give yourself a visual aid, that's perfectly fine. But if those two larger groups are on the same side of the double bond, then we call that the cis isomer. So that will be cis-2-butene. 2-butene because we number the carbons 1, 2, 3, 4. It actually doesn't even matter which side we start on since this compound's symmetrical. So it's going to be 2-butene however you slice it. But that one is cis-2-butene. And then if the two larger groups are on opposite sides of the double bond, we call that the trans isomer. So that one is trans-2-butene. And that's all fine. But you find before too long, this system is easy to break. And all you need to do is have more than two groups, more than two different groups on those double bonds. Or what if something's not an H? Then we need another way to assign the stereochemistry, one that's unambiguous. And that's where this Enz system comes in. So in order to do that one, again, you will need to focus on those two alkene carbons, looking first at one of the alkene carbons and then at the other of the two alkene carbons. It does not matter which one you look at first. You will get the same answer either way. So you don't need to worry about that. You will get the same answer. And what you do, let's start with maybe this one on the left. So I'm looking at this carbon over here, and I see a chlorine attached and I see a carbon attached. And then you just judge those two on the basis of atomic number, which is the heavier element. And so chlorine is a heavier element. I think it's element 17. You can correct me on that. And I think carbon is element number 6. So the chlorine wins. We bear that in mind. And then we look at the other carbon. I see a carbon, which is element 6, and I see a hydrogen, which is element 1. So the carbon wins. The carbon beats the hydrogen, and the chlorine beats the carbon. Now, what if they're both carbons, let's say? Then you have to keep going out another atom. And if they're still both carbons, you go out again, another bond. You will eventually be able to make that decision. And this is all written out for you in the class notes. I have a step-by-step method written there for you. But eventually you will be able to make the determination. You need not worry about getting a question where you can never make the determination. Because let's say that happens. Let's say you keep going out and out and out and out and out, and it's always the same. Let's say you get a problem like that. Well, another way of saying that is the two groups attached to that carbon are the same. And in those cases, there is no cis trans and there is no EZ. So the question is moot. So I don't think you will ever be asked to decide whether something's cis or trans or E or Z if there's two of the same group attached to either of the two alkane carbons. I'll even write it down. If either of the two alkene carbons has two identical groups attached, there is no EZ or cis-trans distinction. Does that help for me to write it down when I say it like that? I'm really trying to be helpful here. There is no EZ distinction or EZ or cis-trans distinction. So I don't think you're going to get that in ALK. The question would be a meaningless question. You can't be asked to decide cis and trans or E and Z if there's two identical groups attached. The groups must differ at some point along the carbon chain, if say it's a carbon chain. And that's when you will be able to decide which element beats the other element. And all you need to do is look at the periodic table and see which element has a higher atomic number. And that's the one that's going to win. So in this compound here, the chlorine beats the carbon because chlorine is a higher atomic number, and the carbon beats the hydrogen because carbon is a higher atomic number than hydrogen. And if the two groups that win are on the same side, the Zane side of the double bond, it's silly, but man, it works. Then we assign the Z configuration. If they're on opposite sides, then we assign the E configuration. So again, if you know any German, Z is for zusammen, which means together, and E is for entgegen, which means over on the other side, or something like that. So this would be Z2-chloro-2-pentene, and I've numbered the carbon atoms for you. 1, 2, 3, 4, 5. Of course, you want to number closer to where the double bond is, if at all possible. And so I think that's the best name for that compound. So that's how you distinguish between stereoisomers. And I do want to mention, you can always use E and Z. You don't have to use cis and trans. Cis-2-butene you can also call Z2-butene. It's perfectly correct. It's not wrong. Likewise, trans-2-butene you can also call E2-butene. It's absolutely correct. Both names are equally correct. Both names would receive full credit. Your choice. That's in some ways why E and Z is the superior method, at least in certain ways. It's also the more modern method, because you can always use E and Z if there's a distinction between the two stereoisomers. Cis and trans is somewhat limited. You have to have a hydrogen attached to each of the two alkene carbons. Good, I might have spent a little more on that than I should have, but I wanted to make sure that I cleared things up from Friday since we were a little bit rushed. Does that make better sense now? Is everyone a little more comfortable with that? Any questions on EZ or cis trans? Not terribly interesting, I'll grant you, but I just wanted to make sure that we clarified that. So one of the things that we need to know about alkenes is that unlike alkanes, which undergo substitution reactions, alkenes undergo addition reactions. And I believe as part of your Gen Chem curriculum, you will have discussed the 4 broad classes of reactions. What? Substitution, addition, elimination, rearrangement. I think every reaction you look at is going to fall into one of those 4 categories. And substitution reactions involve 2 groups or 2 pieces switching places. And that's exactly what we saw with alkanes. We said alkanes can be halogenated with chlorine or bromine, Cl2 or Br2. And you can see that what happens is an H from the alkene switches places with one of the halogen atoms in the halogen molecule. Now, that is not the mechanism of the reaction, by the way. I think I mentioned that already, not that I really care if you learn the mechanism in this case. We will talk a little bit about mechanisms with curved arrows today, just a bit. I'm not going to emphasize it very much in this class, but I do want to talk about it a little bit, so you're at least exposed to the ideas. But certainly not for alkane halogenation. In any case, I think you can see that the hydrogen and the halogen switch places, and you get the halogenated hydrocarbon, and as the byproduct, you get the hydrogen halide, which is inorganic. And again, it doesn't happen that the one molecule comes up next to the other and these two things just like that. There's several steps involved. But conceptually, that's all that happens, is the two groups switch places. And that's what's going to happen in any substitution reaction. And you looked at lots of substitution reactions in Gen Chem, which I hope they pointed out, but I wasn't there to point it out for you, so I have no control over that. But you saw tons of reactions, like all of your precipitation reactions are going to be substitution reactions. What? Lead 2 nitrate plus 2 sodium chloride yields lead 2 chloride precipitate plus 2 sodium nitrate. All that happens is the metals switch places, or you can say the non-metal portions switch places, the anion switch places. Either way, it's the same thing. You have two things switching places. Or acid-base reactions are also substitutions. What? You've got like 2HCl plus calcium hydroxide yields calcium chloride, CaCl2, plus 2H2O. All that happens is the metal and the hydrogen switched places. So that's also a substitution reaction. So substitution reactions are very common, but substitutions are not the type of reactions that alkenes undergo. Alkenes tend to undergo addition reactions. And addition reactions are of this general type. A plus B yields AB. You have two or more smaller pieces coming together to make one big one. And by the way, an elimination reaction is simply the opposite of that, also called a decomposition reaction. So decompositions are of the type AB goes to A plus B. So they're just the opposite of an addition reaction. So an example of the type of reaction we're going to learn is over here. You've got an alkene reacting with, we're going to go over, 4 general classes of reagents that will add across that alkene double bond, and you will get a product that looks like this. So if we're hydrating the double bond, that means we're adding water, and the H will go to one of the carbons and the OH to the other. And you do need an acid catalyst in that case. So we'll go over all that. We'll show you what you need to write and what you need to know about that and all that kind of thing. But that's what we're going to spend most of the class on today, I would say. I do want to be sure to stop by about 225, 230, if at all possible, to mention Markovnikov's rule. But explaining the actual reactions themselves, I don't think will take that long, because they're conceptually very simple. It's just going to be you take an alkene, and you can take any old alkene you want to, and we'll talk about adding halogens across the alkene. We'll talk about adding hydrogen across the alkene. We'll talk about hydration, which is adding water across the alkene. And we'll talk about adding acid molecules across the alkene, which will consist of HCl, HBr, HI, or sulfuric acid. And all 4 of those are conceptually the same. It's the same idea. All that changes is the identity of the acid that we add across the double bond. I will let you know I'm going to go a little bit out of order compared to the book. If I may make so bold, I think my order makes a little more sense. I will also let you know you'll find in this chapter a ton more addition reactions. I don't see any benefit to your learning all of them. I think that would be an intolerable burden that does you no good. As I often like to say, I can't think of any earthly good it would do you to learn all of them. I think if we learn those 4 classes of reactions, you've got the idea. I think that will be enough for us. So those are the 4 reactions you will need to know: halogenation, hydrogenation, hydration, and addition of acids. And again, there's some subclasses to all of them, but those are the four general types. And I might as well I'll probably say this again, but I might as well give it to you up front. Now, what does it mean to know a reaction? It doesn't mean just memorizing an example like this. You might find that helpful, you might not. That depends on your learning style. But it doesn't mean just memorizing the examples from class. Knowing a reaction means a few things, and I can at least describe it in part. I don't know if I can, describe it to every last little detail. But knowing a reaction means, among other things, that if you're given an alkene you've never seen before, and you're also given the reagents for any one of these 4 types of reactions, and I am pretty explicit in the class notes in the syllabus that these are the ones you'll have to know. But if you're given any alkene, including one you've never seen before, and any one of these sets of reagents, which we will go over, you can predict the product. You can predict the major product of the reaction. Again, even if it's an alkene you've never seen before. And it also means, knowing a reaction also means that you can do the exact opposite. That if you're given the addition product of any one of these types of reactions, you can figure out what the alkene was that you started with, even if it's one you've never seen before, and also what the other reagent is, which one of these sets of reagents was reacted with the alkene. And I think the OWL problems will help you in that. I think maybe doing some of the problems in the book will also help you, especially those where you can look up the answers. If you have problems in the book that you can't find the answers, and you've done some work and you want to show it to me, don't hesitate. Please bring it to office hours. I'll be happy to tell you if your answer is right, and if not, what the right answer is. So that's what it means to know a reaction. I just want to be very clear on that, so you're clear on what's expected. It's not simply memorizing the ones from class. That may or may not be helpful. That depends on the individual. But it means if you're given an alkene, even one you've never seen before, and you're told to do one of these types of reactions to it, you can figure out what the major product is. And it also means being able to go in the opposite direction. Good, so I think that's about enough in terms of upfront information. With that, I think I'm ready to present these types of reactions. So, give myself a nice clean chalkboard over here, so to speak. Let's talk first of all about hydrogenation of alkenes. Doesn't really matter the order we do this in. Wait a minute, yes it does. Why don't I do it in the same order? Aha, halogenation, then hydrogenation, then hydration, finally addition of acids. Okay, so halogenation first. I mean, why make things difficult on everyone, including myself? In the halogenation of an alkene, you will start with some alkene. And this, by the way, is going to be how I present the information at first. I'm going to give like a generalized alkene and we'll say anything at all can be attached in those other 4 bonds. Whatever you want, doesn't matter. But you do need of an alkene. And we're also going to react this with some halogen. So X2 is either Cl2 or Br2. With the usual things being true, just like we said with halogenation of alkanes, which is a different reaction. That's a substitution. But there we said F2 is too reactive. It'll just tear the molecule apart. And I2 is too unreactive. It is the opposite problem. If you add I2 to an alkene, nothing happens. Just look at each other. But in the end, you will get the addition product. And each of the 2 carbons that were involved in the alkene will now have a single bond instead of a double bond, and each of the 2 alkene carbons will have whatever halogen attached we're given. So if you're given Cl2, they'll both get chlorine atoms. If you're given Br2, they'll both be bromine atoms. And that's basically it. So essentially, if we're given, I'm just going to make up an alkene. Let's look at some examples. Let's say that we had this alkene, and we added, oh, I don't know, where's my halogenation? There's my halogenation. Let's say that we add Br2. I'll also, by the way, you'll notice that you can also put inorganic reagents like Br2 above or below the arrow. You'll sometimes see it given to you that way as well. That's also acceptable. It's just another way of saying the same thing. In any case, we will simply turn the double bond into a single bond. And I gave you this step by step in the class notes. But you'll turn the double bond into a single bond, and you'll attach one atom of that same halogen to the two carbon atoms that had the double bond between them. You change the double bond to a single bond, and then you add one of each of the two halogen atoms, the one that, whatever one you're given, whether it's Cl2 or Br2, to those two carbon atoms. Do you see how we've changed the double bond to a single bond? And can you see how we've added the two bromine atoms? And I'll do another example as well. Does that make sense so far? Do you see how this falls into that category? It's just a specific example. And we could have taken, I don't know, cyclohexene and added Cl2. Or I could have just drawn an arrow and written Cl2 above or below the arrow. It's the same thing, just another way of writing the same thing. And I would expect that we would get 1,2-dichlorocyclohexane, you could call that. So I've just changed, again, the double bond to a single bond, and I've added the two chlorine atoms that were in the original halogen atom. The mechanism doesn't happen all at once. It takes a couple steps. And we'll talk a little bit about mechanisms today, like I said. And that's basically it. If you're following that so far, then you understand alkene addition reactions. That's why I said actually presenting these reactions is not going to take all that long. But I did want to spend a few minutes making it clear what you'll need to know. Good. Next one. I think hydrogenation was next. Hydrogenation of alkenes. And in a typical hydrogenation reaction, you will add H2 gas, so elemental hydrogen, and you do also need a catalyst for this reaction. Now, some of these reactions require a catalyst, some do not. That's part of what it means to know a reaction. Knowing when you do or do not need a catalyst, and I'm assuming catalysts were defined for you in Gen Chem, you know it's something that increases the reaction rate by lowering the energy barrier. So the catalyst that you need for hydrogenation is going to be either palladium or platinum metal. PT is platinum. It could also, I'll just let you know, it could also be palladium or nickel. And all three of those are in the same column of the periodic table. So it's all three of those coinage metals, so to speak. We make coins out of those metals. Well, platinum coins are pretty expensive, but you get the idea. In any case, in the end, in the final product, the double bond again becomes a single bond. And just like with halogenation, we attach hydrogen atoms. So, of course, if you're using line angle drawings, you don't even have to show the H's. You can if you want to. So, for instance, if we had that alkene again, just to use as an example, and I could write plus H2, or I could even put H2 over here in platinum, or you could write H2 comma PT, same thing. They're just different ways of writing the same thing. And in the end, I would expect that you would get that alkane. So it has the two H's added. And of course, if you're using line angle drawings, you don't have to show the H's. You can if you want to. It's not wrong. But if you're using line angle drawings, remember, H's are understood. So for instance, this carbon over here was a CH2, now it's a CH3. Two of those H's were there to begin with, the other one we just added in the addition reaction. And that's all there is. Conceptually very simple. Addition of hydrogen across an alkene. And conceptually, again, real similar to halogenation. Just we're adding hydrogens instead of halogens. Yes? Well, the platinum's a good question. What happens to the platinum? Answer, at the end of the reaction, it's in the same form that it was at the beginning. So remember, catalysts are neither consumed nor generated further beyond what you're given. In order to be a catalyst, it needs to end up in the same state that it started. So you just recover it from the reaction mixture and in principle could reuse it. No, good question. Other questions? And again, you've figured out by now, owl will be owl. Just so you know, this platinum could also be palladium PD or nickel Ni. Those will all work. Good. So next one, we're going to up the ante a little bit. Let's talk about hydration. And in hydration of an alkene, that refers to adding the elements of water across an alkene. So the concept involves, again, taking an alkene, and now we're going to add H2O. You might want to think of this as HOH, just in terms of conceptually. You do need a catalyst, and that catalyst is acid, and it can be any acid. You might see this written as H2O, H plus, or you might see H3O plus written, same thing. What happens when you dissolve H plus in water? You get some H3O plus ions. They might also give you H2O, well, H2SO4 could be a little confusing. I think this is the way I will try to remember to give it to you, either H2O and H plus or H3O plus, which is the same thing. I don't want to muddy the waters much beyond that if I can possibly avoid it. Though it might be that in some AL questions, I think I remember seeing where they give particular acids. But you certainly do want water to be present in order for this to apply. And it's that water that's going to add to the alkene, and you will again get a single bond, and then attached to one of the carbons, you get a hydrogen, attached to the other, you get OH. So that's hydration of an alkene. The double bond becomes a single bond, and of the two pieces in water, if you think of water as HOH, one of the carbons gets the H and one gets the OH. How do you know which gets the H and which gets the OH? Markovnikov's rule. We'll get to that. Well, I hope to get that in today's lecture. Good. So for now, just for now, I will avoid the issue. Let's say that we took cyclohexene and we added aqueous acid. Whoops. Last I checked, water was a neutral molecule. So you could write H2O and H plus or H3O plus, doesn't matter, same thing. H3O plus means a dilute aqueous acid solution. That's all it means, but it means the same thing. I would expect that you would get that alcohol, and the other of the two carbons that were involved in the alkene will get the hydrogen. You can draw it if you want to. It's not wrong. But if you're using line angle drawings, you don't have to. It's understood. But if it helps you to get that visual aid, feel free to draw a bond and then draw an H. It's the same thing. In other words, the other of the two carbons that was involved in the alkene now has two hydrogens attached. One of them was there to begin with, the other came with the water molecule. So you will get a molecule of cyclohexanol, as that is called, in case you were curious. So that's hydration. And last but not least, addition of acids. And the acids that we will be involved with are HCl, HBr, HI, which actually works this time. HF does not. We'll get to why. And the other one, the last acid you might run into is sulfuric acid, H2SO4, which you might want to think of as HOSO3H. But you see, all of these are H something, HCl, HBr, HI, H sulfate. And as you can imagine, it really doesn't matter which one of these you choose. One of those, you can already see, I think, what's going to happen. We're going to add essentially HX, and we'll say X equals Cl, Br, I, or bisulfate. And just by the way, in case you were wondering, as to how that was connected, I don't think it's unreasonable for you guys to know the structure of sulfuric acid, HO, S double bond O, OH. I don't think that's unreasonable. You went over that in Gen Chem. So that's what SO3H means. It means a bisulfate group. But be that as it may, it really doesn't matter which you choose. In the end, you will get a compound with a hydrogen on one of them. Going to see if I can do something fancy here. See if this works. And yes, as a matter of fact, I am proud of myself. Thanks for asking. So the other will get whatever the other piece is. either ClBrI or the bisulfate group. And you'll just write out whatever it is based on what you're given. Now, I did mention that HF does not work in this. The reason for that is the hydrogen-fluorine bond happens to be very strong. There's very, very good overlap between hydrogen and fluorine because they're much closer in size than H and Cl or H and Br and so on. So HCl, HBr, and HI are strong acids. HF is actually a weak acid because that HF bond is so strong. It's one of the strongest bonds there is. That being said, I don't mind saying by way of a public service announcement, HF hydrofluoric acid is exceedingly dangerous. I hope and pray that you never have to deal with it, but it's very, very dangerous. HF solution will eat glass. So HF needs to be kept in special plastic bottles. I'm trying to remember if in 20, 25 years of, to some extent, doing organic synthesis, I've ever had the pleasure of dealing with HF. Maybe once or twice. It's a distant memory at best, but it's something I respect. Very, very, very dangerous. HCl, HBr, and HI are also dangerous, but for different reasons. And in many ways, nasty as they are, they're less dangerous than HF, though I wouldn't go taking a bath in any of these things, mind you. So if I were to give an example, let's say we treated cyclohexene with, what do you like, HI? I would expect that you would get iodocyclohexene, where the other of the two formerly alkene carbons now has a hydrogen attached to it. If instead we treated cyclohexene with sulfuric acid, well, then one of those two formerly alkene carbons, which now have a single bond instead of a double bond, will attach an H. The other, you would attach the bisulfate group. But conceptually, all four of those reactions are the same. You change the double bond to a single bond, and then on the two formerly alkene carbons, you attach an H to one of them, and whatever the other piece is to the other, whether that's ClBrI or bisulfate. And that's all there is to it. And those are the alkene reactions that I will expect you to learn. You don't need to know any of the others. I think that gives you enough of an idea about how these things work. We don't need to do hydroboration and oxymercuration. Oh, I'm going to die here. I don't see that doing anyone any good. I don't see that doing any of us any good, including me. With this, I think you get the idea. Good. So that's in good timing. In the remainder of the time, I want to talk, again, just a little bit about mechanism. And I'm going to apply it to this last type of reaction, addition of acids. We're going to go over that mechanism since it's fairly straightforward. It is only 2 steps. And so I think for something that has only 2 steps as opposed to, say, 10, 2 steps is not so bad. Won't do you any harm to see curved arrow notation used correctly and for a reasonable purpose. Up till now, the only time we've used curved arrows at all is to help us to see other resonance forms, and curved arrows are about movement of electrons, and resonance is about exactly not movement of electrons. So that's why I got kind of agitated like this, because it's bogus. Here, let's at least a little bit look at non-bogus use of arrows. And I think it will help you understand this reaction a little bit more, and also fold very nicely into the idea of Markovnikov's rule. Good. Any questions on any of those then? Yes. Absolutely does. Markovnikov's rule, we're going to find, applies to cases where both the alkene, great segue, the alkene is unsymmetrical, like this one, meaning like it's not symmetrical down the double bond, and the reagent is also unsymmetrical. Now, if the alkene is unsymmetrical, but the reagent is symmetrical, like Br2 or Cl2 or H2, then it doesn't matter. There's only one possible product. But what if the alkene is unsymmetrical and the reagent is unsymmetrical, like in hydration or addition of acids? That's when Markovnikov's rule comes in. And we'll definitely go over that today. And luckily, at least the way we'll apply it here, I don't think it's too burdensome to learn. Good. Other questions then? All right, wow, I'm doing a lot of writing today. Okay, so let's talk a little bit about mechanism of addition of acids to alkenes. And as an example, let's go back to our, again, for now, you asked about Markovnikov. So for now, I want to kind of avoid that issue, but we'll get to it. Let's say that we added HCl to this. And we get, of course, chlorocyclohexane. I could have picked also HBr or HI or sulfuric acid. Same exact mechanism will apply. The way the mechanism works is we start with our alkene, and the acid molecule is going to line up with the alkene molecule such that the H of the acid, the proton, if you will, is right close by to the alkene double bond. And what happens is the electrons, the 2 electrons in the alkene pi bond, will swing out and pick up H plus from the acid. And then at the same time, we break the bond between the H and whatever is attached to it. So what we're going to get out of this is either Cl minus or Br minus or I minus or the bisulfate ion, one of those 4 ions. It doesn't matter which. The mechanism is the same for all of them. And although you don't have to show the H, I'm going to do it here just for clarity. That's the H that we just added. There's also another hydrogen still attached to that carbon. That's still there too. But we're not quite done, because you can see that we swung these electrons away from one of the carbons. This arrow here means that we're using these electrons to form a bond from carbon to hydrogen. So the electrons that were in the pi bond now are in this sigma bond. But we've swung away those electrons from the other of the 2 alkene carbons. That alkene carbon, to be sure, has a hydrogen attached. But if you work it out, that carbon will have only those 3 bonds and no lone pair. And if you go back to our formula for formal charge, you'll find a carbon atom with 3 bonds and no lone pair has a formal charge of +1. And we call that type of species, by the way, a carbocation. It's exactly what it sounds like. It's a carbon with a plus charge. And the carbocation is the intermediate of this reaction. That's an actual thing. That's a real species. That's been detected experimentally. So that's the first step. And the second step, you'll take whatever anion you've just made. Oh, shame on me. I forgot my lone pairs on chlorine. I have sinned again. There, I've now made up for my sin. So we will also have the chloride ion in this case. And again, that could just as easily be Br minus, I minus, or bisulfate. We'll just take whichever is the anion you were given, and that will now add to the carbocation. That makes sense. You've got a thing with a minus charge. You've got a thing with a plus charge. The thing with the minus charge, the anion, is going to donate one of those lone pairs and use it to make a bond to that carbon, which will also get rid of the plus charge in the carbon. And you will get chlorocyclohexane. Of course, the hydrogen you added is also still there. But now there's no longer any charges. Almost sinned again. 2 sins in one class. Unforgivable. Off with his head. Good, so you get the product then. But it's 2 steps. In the first step, the electrons in the pi bond are used to make a new sigma bond to the hydrogen. And it also loses whatever the anionic piece is, whatever the thing with the minus charge is. And in the second step, you start with that carbocation that you get, and just organic chemists are so violent. We say the chloride ion attacks the carbocation. I'm not making this up. That's the term that we use. I don't know where it came from. It's decades old. And in the end, you get the product. So it's just 2 steps. You'll get to practice that a little bit on OWL too, but it doesn't matter which alkene you start with. Regardless of the alkene, regardless of whether it's HCl, HBr, HI, or sulfuric acid, the mechanism is going to be the same. And by the way, I'll even let you know, we're not going to go over it, and I'm only going to worry about the mechanism of addition of acids. But in case you were wondering, addition of a hydration, addition of water is real similar. It's very, very similar to this. I'm only going to go over the mechanism of addition to acids. I think that's all the mechanism we really need, at least for now. But just so you know, the other mechanism's the same. Halogenation is actually a little different. There's a few more steps involved. I won't say it's like completely contradictory. It's much the same kind of idea. It's just a little more complicated, and there are a few more steps involved. The mechanism of hydrogenation, I don't know what it is, and I have my doubts that anyone really does. Probably very different from this. But if you're familiar with the mechanism of that fourth class of reactions, addition of acids, I'm happy. I think that's enough. And I think that's enough to give you the idea. Good. So it makes us ready to go over to tackle the question of what happens if you've got an unsymmetrical alkene. Here I chose a symmetrical alkene so as to avoid the issue. But if you have an unsymmetrical alkene and an unsymmetrical reagent, how do you know what's going to be the major product? How do you know what you're going to get? And that's where Markovnikov's rule applies. In fact, why don't I just give you Markovnikov's rule right up front, and then we'll show you how to apply it. But Markovnikov's rule applies when you have an unsymmetrical alkene reacting with, I lied. I'll still present Markovnikov's rule, but I think it will not make much sense if I present it absolutely devoid of context. But Markovnikov's rule applies when you've got an unsymmetrical alkene reacting with an unsymmetrical reagent. For example, let's go back to this alkene, which we used once. I think you will agree that alkene is unsymmetrical, unlike cyclohexene, which is symmetrical. And let's say we reacted this guy with HBr. And of course, HBr requires no catalyst. I could just as easily have used any of the other acids. I could also just as easily have used H2O in hydration, because that's also an unsymmetrical reagent, because one's going to get the H and one's going to get the OH, so it's unsymmetrical. So the question then is, which do you get as your major product? Do you get this one, or do you get that one? Both are possible. And the answer, by the way, is you do get both. But which is going to be the major product? Which is going to be the one you get more of? And it turns out the major product is this one. And the minor product is this one. And what you will put depends on how the question's phrased. If OWL says, give the major product, then you'll just give the major product, and you'll apply Markovnikov's rule in order to do that. If OWL says, give all products or both products, then you'll put all of them. So it depends how the question's phrased. But this allows you to, Markovnikov's rule allows you to predict which of the two products is going to be the major product. And Markovnikov's rule, I'll write all this down, not to mention that it's in the class notes also, but I'll also write it down. Markovnikov's rule says in order to make this decision about which is the major product, you look at the two alkene carbons. And you need to figure out which is, as they say, more substituted. In other words, fewer H's directly attached. And I think you'll agree that carbon has fewer H's directly attached. And this one over here has more H's directly attached. And by the way, another way of saying the same thing, you can say that the one with fewer H's directly attached, we call that the more substituted carbon, meaning more substituted with carbons and other groups. And this one is going to be the less substituted carbon, meaning there's more H's and fewer of the things that aren't H's. You can see that, right? This carbon here is one H directly attached. This one has two H's directly attached. So that second one is the less substituted carbon. There's more H's directly attached. And Markovnikov's rule says that when you're dealing with an unsymmetrical reagent, I'll write all this down, but it says that when you're dealing with an unsymmetrical reagent, The H goes to the less substituted carbon, the one with more H's directly attached, and the other piece, whatever it may be, goes to the more substituted carbon. So H goes to less substituted carbon, other piece to the more substituted carbon. Oops. Move chat over here. And that, in a nutshell, is Markovnikov's rule. Whoops, what have I just done? Good. So we'll do it. We still have 4 minutes. We'll do some more examples as well. And by the way, Markovnikov's rule is directly related to the mechanism of the reaction. This is only one way of stating Markovnikov's rule. Another more thoroughgoing way would be to say that you're going to prefer the pathway that gives you the most stable possible carbocation intermediate. And it turns out that the more H's are directly attached to a carbocation, the less stable it is. And the fewer H's directly attached to a carbocation, the more stable it is. Again, you'll get a chance to go over all this in the OWL assignments. You'll get exposed to this idea pretty thoroughly, I think. But this is a much simpler way of, even if it's less theoretically rigorous, it's a much simpler way of stating Markovnikov's rule. And you can rely on it to give you the correct answer. When you've got an unsymmetrical alkene and you're reacting it with an unsymmetrical reagent, the major product will be whatever you get by attaching the H to the less substituted alkene carbon, the one that is more H's directly attached, and the other piece, whatever it might be, to the more substituted carbon, the one with fewer H's directly attached. And that's basically Markovnikov's rule in a nutshell. So what if instead of cyclohexene, we started with 1-methyl cyclohexene? Let's say that we treated this with H2O and H+. In other words, we're doing a hydration. What's going to be the major product? Well, we'll still turn the double bond into a single bond. And on one of those two carbons, we need to put H. One of those, we put OH. But Markovnikov's rule says that the OH, the one that's not a hydrogen, is going to go to the more substituted carbon, the one with fewer H's directly attached. And the H is going to go to the less substituted carbon. So the major product, which is usually what we give, is going to have the methyl and the OH on the same carbon. And the hydrogen is going to go on the other alkene carbon. So this carbon here is now a CH2. Of those two hydrogens, one was there to begin with. The other one came from the water. So your product would look something like this. Call that 1-methyl 1-cyclohexane-all if you want to, or not. I won't lose any sleep. But in case you're wondering how that's named, that's how we do it. So that's how to apply Markovnikov's rule. I wish I had time for a bunch more examples, but I'm pretty much already out of time. But that's how you apply Markovnikov's rule. Good, and that puts us in a good place for starting on Wednesday. I also made the next couple of OWL assignments available. So I think I put them all on Sundays. I think we're in good shape. Other than that, have a great day. We will see you on Wednesday.